Tell you, so I'm John Mailhot. I'm the CTO of Networking Infrastructure at Imagine, and more to the point for this, I've also been working as the editor of the SMPTE 2110 for a number of years. When I started that job, I had no gray hair. Maybe less gray hair, let's put it that way. Couple of things just to highlight about SMPTE 2110. The first is that it's by and large finished. So all the main parts, 10, 20, 21, 30, 40, are published, available on the SMPTE website. How many of you have access to the SMPTE standards? How many of you have read them? You know, it's okay. When you need to, you will. There are a few bits that we're still working on, and I'll cover those as we go. But the main stuff is finished. And that's a big accomplishment as an industry, and it's the whole thing we're going to talk about in this super session this morning is all these parts and what they do, how they work together. Now, 2110 was not developed in isolation. You know, there's an old joke about standards bodies and how, you know, the good thing is there's so many to choose from and there's so many organizations, and people like to think, oh, they must all be working at cross purposes. But actually, the different standards groups, SMPTE and AMWA and so forth, about 5 years ago under the actually guidance of Rich Friedel, I think was the one who really had the vision to make this happen, we put together a thing we called the Joint Task Force on Network Media. And this included SMPTE and AMWA and EBU, the Video Services Forum, AES later joined in as well. And the whole idea was that we worked together, we divided up the work to be done, each organization sort of stayed in its lane, worked on its focus. And this is the Joint Task Force roadmap of how all these parts fit together to move the industry forward into an IP and virtualized future. So it covers SMPTE 2110 and all these sort of, you know, signal level things. It also talks about control plane stuff, including AMWA ISO 4 and 05, which I'll hit this morning. And then it gets on into the future stuff about dematerialized facility. And as you can see, the roadmap is really specific down here when it's in the current term, and a little less specific about the future because, well, we're still inventing the future, and that's as it should be. But we do have a good joint idea of where we're going. Now, SMPTE's been involved in IP transport and IP stuff for a long time. So we had 2022, 1, 2, 3, 4, that's how MPEG transport streams get around on IP. Those were published a long time ago and are used every day all over the world. 2022, 5, and 6 were a, hey, let's map SDI into IP. And there's still situations where that's the right thing to do, and people do it every day. But, you know, each of those is itself a multiplex, and then you put it in IP, and it becomes this bundle. And in production, in studios, usually you don't want that bundle. Usually you want to be able to take the audio over to the audio desk, the video over to the video desk, and they'll meet up later at the end maybe. So 2110 was very different. 2110 said, let's put the video, the audio channels, the ancillary data, all in separate signals in the network so that the audio guy can just take the audio, and the production switcher can just take the video, and the captions workflow people can just take the captions, and so forth. That's the whole idea of 2110. The rest is details. Now, of course, 2110.10 is the first part. It talks about the system timing model. Now, why do you need a timing model? Well, because once you take all those parts apart, you know you're going to want to put them back together eventually. And people get very worried, as they should, about lip sync, equally worried about the relationship of captions to video and so forth. So SDI was great because you had this big bundle, it was self-timed, everything was stapled together in there, and you had to work hard to screw up the lip sync with SDI. Not that it was impossible, but you had to try. But in 2110, once you split it all, every signal has a timestamp. Every packet has a timestamp. And those timestamps reflect the time in, production time that goes with that packet. So when the video is sensed by the camera, it gets a timestamp. When the audio is sampled by the microphone, it gets a timestamp. They're as accurate as they could ever be. We can now measure the time more accurately than is required. And that causes some arguments over very small things that will never matter, but that's part of the charm of working on standards. The beauty of 2110, and the thing you have to keep in mind, is that a 2110 environment is like a synced and timed SDI plant. So everything is synchronous, everything is timed to this big PTP clock. And the good news is that means you can mix and match video from this camera, audio from that microphone, all over the plant, and expect them to line up. But it also puts the burden on you that you have to make that be true. So 2110 is not as, let's say, forgiving as SDI sometimes was. In 2110, things really are synchronized by PTP. And if you have a device that somehow isn't locked to PTP, it's going to not work well in your plant. So good thing we're going to talk about PTP in one of these sessions today. So 2110 says how you use PTP to do all this. It says how these timestamps are calculated, so every microphone and every camera system and every playout server, whatever, will do it the same way so that you can mix and match the signals. It specifies a lot of general requirements that apply across all the parts, including this thing called Session Description Protocol, which is a little tiny text file. It really is text that's readable by people, although you have to sort of know what you're looking at, that tells you everything you need to know to receive a stream. And so this isn't something we made up. This is a RFC. The IETF made it up actually quite a few years ago. And then these SDP files are how the individual audio and video streams and the control system interact. Now, what does one of these look like? Well, it's got a bunch of text in it, and these are English characters, and they are readable. You have to, after you've read a few of them, you start to get the lingo. This one has an error in it. If someone can tell me that error later, you get a free cup of coffee in the back. But all that said, that's all that's in 10. 10 doesn't tell you how to do video or audio or anything. 10 just says, here's the timing model of how all these parts go together. Now 20 is about video. In particular, 20 is about uncompressed video, pixels on IP. There is work going on compressed, and we'll talk about that in a second. But 20 is really uncompressed video. So first off, we only send the pixels that you can see. We don't send the horizontal blanking. We don't send the vertical blanking. If you think about UHD and you say, oh, 12 gig SDI, there's 2 gigabits of blanking in that, right? Like, no one's ever going to make a cathode ray tube UHD display. I mean, there's probably one in Japan somewhere. But other than that, no one's really going to make a UHD display that has a flyback transformer, if anyone's old enough to remember those, and is doing all that. So why on earth are we still sending around blanking? Because it's tradition, and we're traditionalists. So not wanting to get boxed out, 2110 supports really big pictures up to 32K by 32K, because 8K is nice. But think about specialty applications like that ribbon around a stadium. That thing could easily be 32K pixels wide. It's not real tall, but it's quite wide. Nothing in 2110 says that you have to stay married to 1920 by 1080 or all the different geometries we've always had. You can signal any kind of picture size or picture shape if you have a specialty application. And, we're 40 miles from the home of many specialty applications right down the road. So let's find them. We also, coming into this, thought, okay, well, SDI, YCBCR, that's so simple. But as we started through the SMPTE process, of course, all the people from the post world and the offline editing world came around and said, hey, what about RGB and XYZ and ICTCP and all these other cool color spaces that are going on? So, okay, we support all those in SMPTE 2110. You can signal that this is a ICTCP signal if you wish. Also, all the different, 422, 10-bit, 12-bit, 16-bit, 16-bit float, so forth, are all in there. And we would be remiss if we didn't support HDR. So you can signal that the signal is PQ or HLG or standard range, of course. And there's, it could easily be extended if people come up with yet another way to do HDR. Let's hope not. The samples really are packed in there because nobody likes to waste a ton of bandwidth. Now, you might ask, how much bandwidth did we really save by getting rid of the blanking? And, in North America, it's only, 16%. That's not, like going to make a huge difference, but it makes some difference. But our 50 hertz counterparts in Europe, they really got rooked in the old system, right? If you look at the blanking, in order to have the same clock rate, we made this giant blanking in the PAL signals and in the 50 hertz signals. So they're getting back 30% of the bits on the wire. That's significant. That gets you another signal down the path. So all that said, did we future-proof this thing enough? Well, we can go really big. In addition to the stuff about the picture size being flexible, the frame rate is flexible. You can signal whatever frame rate you like. So if you have a peculiar sensor, or if you're doing cinema work that's at 47 point whatever because it's 48, but you're working in somehow a 2997 workflow because I don't know why you would do that, but it could happen. You can signal that. And you can signal all this stuff about HDR, which we all know is going to be a whole topic later today. Now, that said, that was the whole uncompressed world, because everyone agrees on uncompressed pixels are what they are, and everyone agrees that they're good enough. Whether they're cheap enough or easy enough, that's different. So there is work now going on right now about compressed video essences, and in particular, how do we put, compressed signals into this timing model and into this timing architecture? Because, UHD, it's still 10.3 gigabits, which is a lot. Even HD is still 1.2, even after you take out the blanking, or slightly less in 50 hertz countries. So could I use TICO? Could I use J2K? Could I use Dirac? Could I use ABC Intra? Could I use, my favorite codec, MFC? That's the best one, right? And the answer is yes. You can use your favorite codec, and 211022 says generically how to do it. Now that assumes your codec has a way to map into RTP, and then this document says, okay, now here's how you calculate the timestamps, and here's how you set up the timing architecture so that the video and audio and all those parts can stay in sync. Now 211022 does not say you will use this codec, because that's the path of doom in standard speak, right? If you start saying, we will use this codec because it's the best one, that's a doomed conversation, right? So there's lots of good choices and lots of bad choices too. And ultimately how this will play out, I didn't even list VC2, but that's actually one that people talk about using as well. So we attacked the problem squarely by saying, what do we have to define in SMPTE? We defined the timing relationship. How do you specify how these timestamps work so that when you use your favorite codec, you can get it timed in with the video and audio and other parts that are already in a 2022 or 2110-whatever environment. And so that's work in progress. It's actually out in pre-FCD comment right now. If anyone's a P member or a observing member of the 32NF, read the document, comment on it. John Fletcher of BBC is actually leading the charge on this. Now, what about audio? Well, there's a whole session about audio later today, so I'm only going to talk the tiniest bit about audio. There is a 2110 document about audio, and in fact, because everything's better in stereo, there's two of them. The first one's really about PCM audio. Now, the only important thing about 2110-30 is that it's built on AES 67. Now, is that important? That's really important, because we didn't want as SMPTE to reinvent how audio worked when the AES had just spent years developing AES 67. AES 67 is a great system. A gentleman's going to talk about it later today, so I'm not going to steal his thunder about that. 2110-30 says use AES 67, and it applies a few constraints. Now, as he'll cover in his talk, AES 67 is like a Chinese menu of choices. So you get to choose your, how many samples you pack in a packet and things like that, and there's pros and cons to all those things. Now, as a television guy, this is how I see audio. There's some microphones, there's a dude over there with a million buttons that makes the production switcher look easy, and in between, Lord only knows. And I'm gonna just skip because I assume that Mr. AES67 is gonna cover this in gory detail. Now, the other thing to remember is audio's tiny compared to the video. That doesn't mean you can step on it. In fact, quite the opposite. It's easily damaged in the fracas, but that's a thing to remember. Now, PCM audio, pulse code modulation, that's all that this -30 deals with. And frankly, that's all AES67 deals with, is good old real audio. That's a trademarked phrase, sorry. Good old actual sampled audio that comes out of microphones and all the things you're used to. Well, there is a lot of use in the television industry of non-PCM audio for things like Dolby E, for things like some of the new object audio stuff where there's metadata channels that are flying around on AES3s. So we did want to have a way to accommodate those other things. So that's where this 211031 comes about, that it handles non-PCM audio. It handles the AES3 applications where people have buried things in the user bits. If anyone's done that, there you go. It also, there's applications that actually use the C bits and the V bits as well. And so if you have an application that requires it, -31 is your friend. -31 is actually built off of a technique developed in the Ravenna consortium. If you're, maybe the AES will talk about that. Now these 31 streams really transparently map what's in an AES3 through the network. So all the C bits, V bits, you name it. As a side effect, they're always at least in multiples of 2 channels because that's how AES3 rolled. Now a little bit about ANTS data, the forgotten stepchild of SDI. We have this great big space, it lives in that blanking, we took away the blanking, so what do we do with it? Well, it gets its own reality. 211040 says how to do it and what to do with it. There's lots of stuff buried in the ancillary data, more than anybody knows, because there's lots of vendor-specific protocols up there. There's probably industry-specific protocols. I wouldn't be surprised if some of the agency customers have agency-specific protocols that are buried up in the VANTs. We didn't want to leave any of those behind, but at the same time, it's not like there's a giant index of them either exactly. I mean, there is a registry of the DIDs and SDIDs, but even that, sometimes people just do stuff. So some of these signals are really tightly bound to the video, like the HDR metadata that's going through SMPTE right now. That better be frame accurate or things can look ugly. Some of them are really just separate essence that's along for the ride and has at least a loose correlation or maybe not. And some really are just, hey, a convenient way to get there. Audio is actually technically a form of ANTS data. Please don't use 211040 to send audio because we have a perfectly good way to send audio. But the standard doesn't say you can't do it, just because somebody objected to the standard saying you shouldn't do it. So it says you can do it. So the IETF actually, in parallel with SMPTE, developed this mapping for ANTS data packets into IP, and the mapping doesn't care what's in them. So we map these ANTS packets into IP and back out without having to know what's inside them, which means that if you have a specialty payload, you have some odd thing, maybe you're in some agency where you've developed some special thing in your SDI or what in your VANTS packets, it all gets there. There's no, the senders and receivers don't have to understand what's inside the packets to put them on IP and get them back out. And that's a good thing. So this 211040 says how to use this IETF thing and a few constraints about it and how to fit it into the timing architecture of 2110, because remember, that's how you keep things lined up between the video and the audio and the ANTS data. So simple enough. Now, what does this mean in practice? Because for years, we've been able to break away audio from video and recombine them, and we all have kind of a sense in production of what that means. But what's it mean to be able to break away ANTS data? Well, if you think about a broadcast chain in the back of your studio, you make your program. Before you can distribute it, right now you loop through all these VANTS inserters that put on triggers and downstream stuff and maybe a few ad markers, so forth. In typical broadcast plant, there might be 6 or 7 things that you loop the signal through that are just tacking more stuff into the VANTs. Well, you don't need to do that anymore. Now, if you want to make SDI, then you can compose it from all the parts. So the things like these, IP to SDI gateways, they might have a bunch of these 211040 receivers and receive timecode, receive captions, receive triggers, so forth, and then merge them all into the downstream SDI. That's neat, right? So your system starts to look like this, that you might have signals in the network that are video and audio and some ancillary data that maybe came from from SDI. Your captioning system, instead of being a loop through of VANTs, now it just generates the captions from the caption files or all the ways it happens today. You might have your downstream trigger system coming from automation that also is generating these scuddy triggers to put in the feed. You might have your test signal generator that's cranking out timecode all day long, and it's another signal floating around. And then if you need to make SDI, all those things get pushed into it. No more looping your air chain through a bunch of single point of failure inserters. This is a pretty good deal. So think about it, because this is a radical departure from the way we do it today that's enabled by IP. Now, is 2110 the universal perfect solution for every situation you're ever going to run into? There's people who, maybe they have marketing roles, but there's people who do try to say things like that. And, it's really not true. Coffee cups are not the universal solution for all beverages either. So 2110 is a great solution if you're building a big OB truck, if you're building a large-scale, studio complex, if you're building like a distributed campus venue production kind of thing. If you look at large-scale college sports, 2110 fits pretty well there. But they tend to be, remember I talked about it being a synchronized system. So it tends to be the same kind of environments where it would be practical to run Blackburst to everybody. Because fundamentally, 2110 is a synchronous system. There's PTP going to everybody. Could you run PTP between New York and Los Angeles for some crazy reason? You could probably get that working, but I wouldn't want to bet my farm on it. That's not a great way to go about it. That's kind of using the wrong tool for the wrong job. 2110 is not actually an ideal solution for everything, right? Few things it's not great for. It's really not very good for getting to and from the cloud. I mean, ignoring cost of bandwidth, which, by the way, you can't ignore cost of bandwidth. There's also the whole notion of, does the cloud even have PTP? PTP is not like hot and cold running water in AWS or Azure or anything. Maybe it will be one day, but this isn't that day. If there's any cost sensitivity to the links, then you really should be using J2K, JPEG XS, whatever. There's a lot of solutions to cost sensitivity of links, and you should use one of them. Distribution systems, like going from network to affiliate, 2110 is probably not a great solution to that, all in all. And really, anytime you're interchanging between arm's length unrelated parties, like say you're pulling a truck up to a stadium. Well, if you've ever been on either the truck or the stadium end of that handoff, it's, that 2 hours of chaos that has to end in 2 hours because the game's starting in 4. So that's not the time to be doing a PTP integration between the truck and the stadium necessarily. There's times and places where maybe this isn't the most perfect solution. My personal belief is that venue patch panel is going to be SDI for probably until I retire. Maybe I can time my retirement to that happening. But anyway, so 2110 is great for building buildings, building plants, building campuses. It's probably less ideal for some of these other situations, and that's not a dig on it. That's not a problem with it. It's just acknowledging that in the same way that the coffee cup is not the universal beverage container, 2110 is not the universal solution to every problem in the world. Now, 2110 is all about the bits on the wire, but what about the bits of control? How do I talk to all these senders and receivers? Because, you know, IP is different than SDI, right? In SDI, all the action happened in the cross point, right? All the action. There's no visible clock in this room, by the way, just as a warning to every other speaker today. All the action in SDI happens inside the cross point. So signals go in, signals come out. When you say switch, something happens inside the cross point. The receivers downstream, they just eat whatever comes down the wire. They don't know that it changed. If the switch is clean enough, they really don't even know it switched. So that was nice. That was SDI. In IP, the receivers are part of the puzzle. The receivers are part of making things happen. So the control system tells the receiver, hey, switch to this new signal. It might also tell the network to do something, but fundamentally, the receiver is part of the equation in this IP stuff. So the control system tells the receiver the multicast groups and port numbers. It also tells it the whole bunch of metadata. So all that stuff that was in that SDP file, that's all stuff the receiver needs to know to correctly interpret the signal it's about to get. Can the receiver guess some of it? Yeah, but guessing is not the same as knowing. So the receiver is responsible for how it does this transition. So you might have, say, an AJA box on the back of a monitor that when you tell it switch to a new signal, it drops the old signal and puts up the new one. You might have a master control switcher or some other thing that when you tell it to switch to a new signal, it gets the new signal, cleanly transitions to it, and then drops the old one. Either of those models is possible. There'll be a wide marketplace full of products that do it one way or the other, and that's the way that works. Now, that's all good, but remember what we just said, the receiver's part of the solution here. So how do you find all those receivers? Because it's not, SDI frames don't jump out of the rack and move around, but cameras can jump out of a shelf and wind up down in Studio 3 and someone plugs it in, thinks it's going to work. So in an SDI system today, you make a lot of manual entries, you build a database, you define all these signals. Hopefully it gets maintained along the way. In IP, in principle, it could be harder. In fact, some of the early IP systems, there's spreadsheets full of IP addresses. Nobody wants that. Nobody wants to go there, right? So ideally in an IP environment, you want to have a way of finding all the stuff automatically or semi-automatically. You want to be able to do stream switching requests in a kind of a standardized way, and so that's what we've been doing over in AMWA. This is a SMPTE meeting, but I'm going to talk about AMWA for a minute, because that's where the control side of this has been going on. So the Advanced Media Workflow Association created a spec called ISO 4. So it defines devices as, things that make and eat signals. Technically, they're called senders and receivers. So when your camera gets taken out of the closet, walked over to Studio 5, plugged into the wall, it gets an IP address by DNS or DHCP, the same way your computer does. It looks up in DNS the same way your computer finds google.com. It looks up in DNS to find the registry service. And then it registers with that registry service using HTTP, the same protocol your browser uses to talk to things, and says, hey, I'm Sony F55, serial number blah, blah, blah. Here's my system ID, and I'm here now. And he might have been somewhere else before, so as a controller, you better figure that out. But that's nice, because now the camera registered into the network, so the controller knows that, oh, hey, that camera turned up in Studio 5 and does whatever it's supposed to do about that. And then anything that cares, like, say, the control system, can look in that registry and can find out all about the devices that are out there and their streams that they might be making, and can, more importantly, subscribe to the registry so that if anything changes about any of those devices, it gets updates that says, hey, that camera moved, or that microphone reappeared over here, or things that happen every day that drive you crazy. Now, what's in this registry? Well, there's some stuff here. There's nodes, devices, And then we map things into senders, which are things that eat streams from the network, or send streams into the network, and receivers that extract streams out of the network. And that's pretty simple nomenclature, really. And then there's flows, which are representations of the content. This gets into the AMWA content model. And sources, which are the original content. So you might have a camera that's actually available in multiple versions, maybe different compression systems or whatever. They would show up as separate senders but trace back to the same source, so that you could tell in archive that those are really representations of the same thing. Now, that's all nice for finding stuff, but how do I do this control trick of telling receivers what's happening? Well, there's another related standard, specification ISO 6, where there's controllers, which aren't really specified there, but it's a logical concept, that know about all the streams from the registration service. They maintain the names, all the stuff we do in routing world where things have names. Maybe they have production-specific names. Maybe they have generic names. Usually they have both. And eventually, they boil those requests down to telling the receiver what to do. And then, of course, the senders and receivers that actually make and eat streams, they register and they respond to these ISO 5 connection requests. That's all good stuff. So when you switch a signal in an IP system, what happens? Well, what happens in SDI? I say, hey, take camera 7 to monitor 3, and I hit a button, and sometime later it happens, and I get a status. Status is important. Well, in IP, what happens is that routing control system through ISO 4 and 5 says to the monitor, hey, monitor 3, switch your video to this new signal with all this metadata. And sometime later, monitor 3, 2 things happen. You get your signal, and the monitor, status is in there saying, hey, by the way, I did that. And then, of course, the control system has to turn that into a human meaningful status, because the last thing you want to do is show operators multicast groups and expect them to mentally turn those back into video and audio signals. And then ultimately, in the middle, there's the network. So the monitor did an IGMP leave and an IGMP join, and that might trigger some things on the network controller. This control system may have directly told the network some stuff as well. Amar is going to talk a little bit about the different ways that that can happen. But fundamentally, to an operator, routing is a high-level concept. I want to connect this source, which might be a whole group of things, a video and some audios and some ANS datas, to a destination that might want some or all of those parts. And I want to get a status that says it happened or that it didn't happen, and I want that status to be true. That's what operationally people want. But under the hood, there's a lot of things that have to happen to make that all happen. And that's where this AMWA ISO 4 and 5 fit in, is really tying that together. Now, could you build a 2110 system without NMOS, or NMOS is another name for ISO 4 and ISO 5? You sure could, and people have built systems, and there's systems rolling around right now like that. It means the control system has to write a driver for every device it talks to. As a vendor, I'll tell you, we hate writing drivers. And as a customer, you hate asking us to write drivers. Well, you hate getting billed for it anyway. So we all want to stop writing drivers. That's what ISO 5 is about. And there's always a danger when you start writing drivers that, they fixed their software, now this doesn't work. But any practical system over the next couple years has to handle a mix of ISO 4.5 things and non-ISO 4.5 things, because that's the reality of the situation. Sometimes you have to handle streams that show up from sources that maybe you don't know much about, because, again, that's kind of the reality of the situation, at least for the near term. There's usually some integration with SDI routing in your plant, because, again, that's how things roll in there. And you might even have to integrate with other parts of the environment through routing protocols, because if you think about your multi-viewer, right? How does the UMD get filled in? Oh, well, it was watching some routing protocol to know what was routed to there. Oh, how does the tally lamp work? Oh, the tally system noticed that somebody routed this signal to the switcher, and that the switcher took that, and that's on the program bus. That's why that tally's red. Well, there's a system that's looking for that information from the router, and it's looking for it in Leech protocol, it's looking for it in Grass Valley Native protocol, it's looking for it in one of those wonderful legacy protocols that's how the world works today. So you can't just ignore the fact that the whole system has to integrate using these legacy protocols. Maybe we'll have better legacy protocols to talk about in a few years, but that's how it works. So fundamentally, in routing, you wind up with a control system that above it, to everybody up here, looks like a router, and then makes and statuses and all that, and below has all this IP stuff. And more importantly, has ISO 4 and ISO 5, and maybe a little Ember Plus, you know, other random protocols to talk to all these devices. But above, it's speaking, you know, LRC, XY, NV9000, GV native, you know, you name it. There's a lot of traditional protocols up here, and being able to separate the traditional stuff from the new stuff is how we can move forward piece by piece without having to reinvent the entire world all at the same time. So how open is this AMWA NMOS stuff? Because people use the word open and they mean a lot of things. Well, it's free, like really free. You know, you can download it today. And more importantly, there's a couple of open source implementations, including one from Sony. So have at. There's also one from Riedel if you like German better than Sony for whatever reason. And there's others yet. There's probably, I think, 4 now open source implementations of these protocols. Like 2110, you know, is this the solution to all the world's problems? No. But it does solve 2 problems that we care about, which is finding all the parts of the system and telling them what stream to switch to next. So now, there's also an ISO 6, and I'm going to just mention it because Amar's probably going to talk about it more. ISO 6 fits in this same model, but says, hey, you know, sometimes you want to tell the network what's going on also. Because if the network is simple, you could probably get away with just IGMP. But most networks don't wind up being simple, even though maybe they started out trying to be simple. So ISO 6 lets the routing control system, which knows the fundamental thing the user's trying to do, it lets it tell the network directly, hey, somebody's trying to connect that thing over there to that thing over there. And then the network can say, yes, I can do that, or no, I can't. Because IGMP doesn't have a great way to fail. It basically, it always tries to succeed, which may not be the best thing. So ISO 6 lets the network keep track of bandwidth and bandwidth utilization. So if you build a network that's blocking, meaning that there's not enough bandwidth to necessarily do anything you could ask for, then you probably want some approach to network control and something like ISO 6. And in the same way that ISO 5 is a universal protocol for devices, ISO 6 is a standardized way for the broadcast controller, routing control system, whatever you want to call it, to talk to the network controller and deal with these blocking situations. It also plays a role in setting up input policing and QoS. So all that said, that's the story of 2110, where we got to. Did I finish with, I left time on the table? No. Oh, wow. Well, if you thought I talked fast, you haven't met Amar. So I can take, I'll take a few questions, but I don't want to go from early to late. So you were quickest in the back there, or in the mid.
2110 was not ideal for transmitting from a network origination facility out to its affiliates. Could you speak as to why?
Well, so 2110 is built on the concept that the senders and receivers are in the same time base. And so while you could imagine that a network, say, you know, CBS or somebody, and its affiliates, all 200 of them, are all GPS locked and everything's golden, you probably don't want to build the whole world based on a failure mode of that not being true. So like right now, we do network to affiliate on satellite, but every affiliate is really responsible for its own time base. So if the affiliate's GPS antenna gets struck by lightning or whatever, they'll drift off and they'll pull it back together, but things will work, and you'll keep television working, and more importantly, somehow that lightning strike didn't take out the satellite dish next to it, so you still have your signal on the air, your programs still run. 2110 really is built on this concept that everybody, the senders and receivers, are in the same PTP domain, locked to the same traceable PTP master. And so you want to shy away from situations where that might not be the case or might be hard to maintain in all possible failure modes. Not to mention, it's also in the uncompressed form, just a lot of bits. And while you could get that bandwidth from New York to Chicago, it's not necessary that you're going to get that bandwidth from New York to Bangor, Maine. Although more and more you can. Hugo, you're dying to ask a question.
How are you going to get all of these switch manufacturers to adopt a single network controller?
Thankfully there's not that many switch manufacturers. There's 5 depending on how you count. There's Juniper, Cisco, Arista. Used to be Brocade. They're part of Extreme now. Mellanox, Huawei. But you'll run out of major switch vendors before you run out of fingers. If you're talking about things with 100 gig ports and a reasonable scale. Will they all adopt this ISO 6? We'll see. Will they all adopt, will all the equipment vendors in the industry adopt ISO 5? We'll see. I think there's benefits to it, and time will tell. It's a marketplace.
So really
I think some will. Certainly, if you look at the participation in the committee, Arista, Cisco, and Mellanox at least have been participating pretty directly.
So you mentioned 2 different flavors of audio, but I've got 2 that I didn't see here. One would be direct stream digital, which is non-PCM, and it doesn't fit in AES-3, and a lot of the audio industry uses it, and in our hybrid plant, we have to deal with it. And the second thing would be something that does go over SDI, which would be MADI. I didn't see MADI in here at all. How would those be handled?
So MADI, you would, and you didn't even bring up Dante, by the way, which is
one at a time.
So MADI is we opted not to make a direct mapping for MADI, but you can take what's in the MADI and map it into the -31 pretty straightforwardly, but it does, you have to sort of take it apart and put it together a little bit.
It's basically a bunch of AES-3s.
Yeah, right, exactly. So there's so you can do that. In fact, that was a use case that NHK brought up, was how to do that. So they actually wanted to have a support for like up to 64 channels, which we added. The direct stream digital, I don't know. Dante has been building an AES-67 compatibility mode into many of the Dante devices for a couple of years now, so depending on the age of the device you have, it may support that. As for the control integration with Dante, that's a good conversation to have over beer in some bar somewhere. But it is, as an industry, we recognize that and we're working it hard. In the orange.
So the question about AMWA and OS 4, 5, and 6 is, since it's an open specification decoupled from 2110, how do you prevent the Linux problem of everybody's open source is different once they start to integrate it?
Well, the spec is, there's only one spec. Yes, there's implementations. Just like in 2110, there's lots of implementations. So there are these interop events that happen a couple times a year. There was one in February in Houston. There'll be one at Riedel in Wuppertal, Germany in the third week of July, second week of July, sorry. So these events happen. All the vendors show up and they test 97 ways. As for the AMWA specs, there's also a fair bit of work going on automated testing. So literally, scripts and computer software that tests, using the API, all the different ways that it can be used, and reporting back if it worked, responded sensibly in all those ways. They're designed to be testable. So I'd say there's a lot of, focused effort on the part of vendors to make sure that happens. Are all the, open source implementations, wonderful and perfect? No, some of them are just examples. Some of them are full-fledged products, or at least could be turned into products. But I think open source is a whole interesting topic in itself. Of should you bet your broadcast plant on an open source thing? Well, maybe not. It's a management choice. You have to look at who's really sponsoring the project. Is it well supported? Can I get support from my vendor even though part of it is open source? Those are all non-technical questions, but really important questions. Okay.
Some of these AMWA components, like the registry, where do those actually live? Is there like a server that sits on the network that manages all this stuff?
Yeah, the registry runs in a server just like DNS and other things do. It's relatively lightweight. Depending on the size of your plant, you would pick a size the server it runs on appropriately. And there's 3 or 4 different registry implementations already exist.
And those are things that end users would typically install themselves on their own servers. There's not a company that's making the server to do such and such, or maybe there will be.
My guess is that the registry will probably get be a side effect of the routing control system. So if you get the Imagine routing control system, we would if you didn't have a registry, we would bundle in maybe the Sony registry or something. It depends which one we pick. But the registry is a necessary evil. Nobody is going to try to make money making the registry, but the registry is like DNS, right? You need it in order to get off the ground. So, okay. Amar, tag, you're it.